Recording is rolling. So welcome to Monday, new week. Uh, guys might remember back on Friday, we were putting together this very long frame. And so I'll give you guys time in a few minutes to finish that. The premise was you were trying to solve an economics problem, which was where to locate a factory to minimize transportation costs. Suppose there's a couple of inputs. Maybe you're trying to manufacture pencils and you need wood from a forest and copper from a mine, and then you're going to ship these finished goods to this town over here. Where should you locate? Well, probably closer to where you'd want to shorten the path that has the highest transportation costs, and you represent transportation costs in terms of weights, so you can actually use this physics setup to solve this economics problem. So we'll come back to that. I'll give you guys about half hour later to finish that. But what's going on later this week? Tomorrow, I'll set you guys up with a friction lab. Now, the deal with the friction lab is, I actually printed this on a page that you guys probably already have. So, you guys remember doing this Atwood lab? You guys remember that? Okay. So, you guys already did this, turned it in, I graded it, I gave it back to you guys. I thought it was a good idea at the time to print friction on the other side. So if you still have this paper, then hold on to this because you're going to need this tomorrow. It says friction lab. If you lost it, then I do have a few extra copies, but that's what's coming up tomorrow. Wednesday, we'll go over some chapter 6 questions from the book, talk about that then. And then Thursday, we'll actually start to move on to the next topic. Now, the way your book organizes, and AP does the same thing, which I'm not used to doing, so we'll figure this out. But what both your book and AP for that matter do is combine a couple of topics, do like a little bit of rotational stuff and also universal gravitation, just all kind of shoved into the same chapter. So do you guys remember if you're in a car, there are 3 things that you can feel. Like you can't feel the speed of the car. This is one of these ideas that keeps coming back in this class. You can feel the gas pedal being slammed down, you can feel the brake, and what was the third thing you can feel? The steering wheel, right? You guys remember that? Now, so far in this class, we've talked about like forces and accelerations. We've talked about the gas pedal and the brake, speed up or slow down in one dimension. But what about bringing in the steering wheel? Well, that's what we're going to start bringing in by the end of this week. I'll have you guys do a lab. You guys will. One thing coming up. You guys remember back on Friday, I gave you guys an open notes take-home quiz on forces. So some of you guys might have that finished already. If you finished it, then just you can turn that into the grade tray. If not yet, then you guys got a few more days to do that. I just gave you guys back your homework too, so you can use that as part of your open notes. And well, this very last note at the bottom here is for 5th period, but you guys probably have 5th period. So federal impact forms. Remember to get those in this week. So I got a couple of warm-up problems for you guys to get you guys more of a physics mindset, and also you guys have got a couple of quiz questions that are kind of close related to these. So got one Atwood and one car break into a stop. Let's start with this Atwood right here. This classic double elevator Atwood. Can you find the acceleration and furthermore the tension in the string? I don't know if you guys can read these, kind of small, but I've got 14 kilograms versus 15 kilograms. 14 versus 15 kilograms. Hey, those masses, they're different, but not by very much. So do you think the acceleration of the system is going to be pretty close to free fall or very, very slow? What do you guys think?
Very slow.
Yeah, very slow, because they're almost the same mass. Well, let's figure out exactly, let's quantify this. And before I even check away with any numbers, I'm going to guess maybe like 1 meter per second squared or less, probably somewhere in there. So when we get an answer, we can go back and check and see if it makes sense. Let's look at a free body diagram, FBD, because that's how we're going to start these things, right? So if you can locate the forces and the masses, then you can figure out acceleration going through Newton's second law of motion. That's the way we've been doing this for the last couple of weeks. Okay. So frictionless, massless pulley. I got a 15 kilogram block versus a 14 kilogram block. Let's locate the forces on this. So this now I'm going to exaggerate this a bit. Well, I do know the biggest force on the board is going to be this one, which is about how many newtons, as long as we're on Earth. You guys remember that weight is equal to mg, mass times gravity field? kind of a backwards way of thinking of it, but it's a quick way. So 15 kilograms times about 10 meters per second squared, wouldn't that be a gravity force of about 150 newtons? So we'll call it that. This 14 kilogram block has a weight that's just a little bit less than that. And again, I said I was going to exaggerate this a bit, so draw it significantly less, although it's not exactly the scale, but wouldn't that be 140 newtons? Right, is it okay? And the reason I'm exaggerating this a little bit is because there are also a couple of tension forces, which are actually the same magnitude. I've been calling this the Goldilocks force. It's shorter than the big force, but it's longer than the small force. But it's the same on both blocks. Such that there's a net force upward on the small block, and there's a net force downward on the big block, because this whole system is going, it's accelerating clockwise. Right, so to get the first question, what's the acceleration of the system? And you guys remember that, well, tension is just internal, so let's just focus on the weights. These weights are what's going to drive the net force and therefore acceleration of the system. Newton's second law of motion. Acceleration is net force acting on some total mass. And I got like a tug of war going on here. I got 150 newtons versus 140 newtons. Well, the difference of those, 150 and 140, that difference would represent the net force. And how much total inertia is being moved around? Oh, the sum of the masses. That's 15 plus 14 kilograms. So I have a 10 Newton net force acting on 29 kilograms of mass. See what that divides out to. What is 10 Newton net force acting on 29 kilograms of mass? Ooh, that's a really tiny acceleration. But that's good, because before I even started doing any kind of math at all, we were saying, well, since these masses are very close to each other, it should be a very small acceleration. And it definitely is. About 0.34 meters per second squared. Tiny acceleration. So it's speeding up, just at a very slow rate. There was a follow-up question. What is the tension in the string? Now, do you guys see that the tension is going to be bounded by these two weight values? The tension has to be more than 140 newtons, so that there's a net force up on the small block, but also less than 150 newtons, so that there's a net force down on the big block. It's somewhere between those two values. And the way you can get the tension is just to focus on one of the blocks and set up a free body diagram for it. Well, we have a free body diagram, so let's finish the analysis on it. So maybe I'll take the 14 kilogram guy, just a coin flip, just pick one or the other. So just hone in on this. And I'm going to say acceleration is net force on total mass. Okay. So we're back to Newton's second law of motion, except remember before I set up this formula, but the way we applied it was for the system as a whole, considering both blocks. But now I'm just going to focus on one of the blocks, and I pick that one randomly. So I see that there's some mystery tension pulling up. There's 140 newtons of weight pulling down, and that's going to drive this 14 kilogram block to accelerate how much? Well, this is just what we did all this for. This much. This is how much that block's going to accelerate. 0.34 meters per second squared. We just did a bunch of work to get that. Okay? So do some algebra. Can you extract t from that? So multiply 14 kilograms up. Looking at, it's about right, 4.83 newtons is equal to tension minus 140 newtons. Add 140 newtons over. The tension on the string must be 144.8 newtons. Hey, remember how a few minutes ago we were saying tension must be the Goldilocks force? Must be more than 140 but less than 150? That's a very narrow window, but it definitely is. It's right in there. So that the small block accelerates up, the big block accelerates down, because that's the direction of those respective net forces. You guys get that? And then the other warm-up question I got for you guys that looks a little bit like one of your quiz questions, but maybe it's a little bit different, but that you guys can figure out. I've got a car braking to a stop. I gave you the mass of the car. I gave you the initial velocity of the car moving forward, let's say the right direction. and I gave you the braking time, the time it takes to come to stop. Okay. If you know that, can you figure out what is the coefficient of friction between the tires and the road? Okay. This is going to be one of those two-part questions where you have to combine everything you know so far in this class. So coefficient of friction, that has something to do with the rate the car slowed down. Like if the coefficient of friction was more or less, see if you can play around with variables in your head. This is one of the skills you can get out of this class. If it was more, I bet this car would come to a stop faster. And if it was less, I bet it would take more time. So this is really an acceleration question. Well, that's the middle step, right? This is going to go through acceleration. That's going to connect the kinematic motion to the dynamics and ultimately the coefficient of friction. So let's start with the kinematic stuff, because I bet you have 3 kinematic values. Can you guys spot 3 kinematic values? I see the initial speed of the car. I see a time. And, what's the third one? Third one's a little bit hidden.
Final velocity.
Final velocity. Yeah, Josh has got it. Comes to a stop. Final velocity must be 0. All right, so great. Let's do that. Let's figure out what rate is the car slowing down, and then we're going to use that to ultimately answer the actual question, what's the coefficient of friction? So, maybe I could do this one right here. Final velocity equals initial velocity plus AT. I mean, if time is involved, because it gave you the stopping time. So, remember going to rest, that's 0 meters per second. Coming from 20 meters per second. That was the initial velocity of the car. What rate is the car slowing down? That's going to be the middle step to help us get to this other question. And this all happens in 3 seconds. So subtract 20 over. Divide by 3 seconds. So acceleration is negative 20 over 3 meters per second per passing second. That works out to about negative 6.67 meters per second squared. Okay. So we're part 1 down, part 2 to go. 1 down, 1. So how does that relate to this coefficient of friction? Well, coefficient of friction. I know that relates friction force and normal force. So maybe what I should really do is draw a free-body diagram for this car, braking to a stop. Free-body diagram. Right, check this out. Stretch of road, solid underneath, car, initial velocity. Okay. But free-body diagram, I don't really care about velocity so much as I care about forces. So this car has a weight straight down. I'll call it mg. The car has a support force from that horizontal road acting straight up. It's called the normal force. And as long as the road is horizontal and there's nothing crazy going on, that is equivalent to the weight. And then if the car is braking to a stop, what's the last force I have to draw? Which direction does it go? To the left. There's a friction force due to friction. Okay? And I know, I'm sort of honing in on what I'm trying to get. Coefficient of friction, I know, is the ratio of this force to this force, the ratio of those magnitudes. Okay? So did I draw my picture exactly to scale? I don't know, but we're about to get this. So let's do Newton's second law of motion. I know that net force is equal to mass times acceleration of the vehicle. But hey, look at that free-body diagram. There's a good reason to draw that out, which we just did. What is the net force on that car? I see the vertical forces cancel out, don't they? As its weight and a normal force. Goodbye. Which just leaves what? Friction force. Isn't this right here the friction force? Friction force is what's causing that car to accelerate. In this case, like accelerate backward, it's going to slow down. But I mean, if it weren't for the friction, the car would just like slide across ice or something, right? That's like hydroplaning. But friction force, you guys have a formula for that too. Here it is. Here's the connection. This is equal to coefficient of friction times normal force. Coefficient of friction times normal force equal to MA. Gave that to you guys all over in your notes last couple weeks. It's also been, you guys have actually had that formula since the first day of class. You guys remember this page? It was on your desk the very first day you walked in this class. It's right here, right here. Friction force is coefficient of friction times normal force. Well, as long as you're talking about kinetic friction, so do a little shortcut here. Okay. And the normal force. Hey, Isn't that equivalent to the weight? Talked about that already, so I'll go ahead and make that substitution. Coefficient of, right, times mg equal to ma. Right, so this expression is what's causing the car to slow down. The mass of the car cancels, which is something you saw last couple of weeks too. So that whole 1900 kilogram actually has nothing to do with the problem. I could make that any number, wouldn't change it. The acceleration of the car is gravity times the coefficient of friction. So coefficient of friction ends up just being a divided by g. And if the acceleration was, well, the number we got was a negative number, but besides that, where'd it go? Remember, it was 6.67 meters per second squared. A negative just tells the direction. So just to take the absolute value of that, I'll call it 6.67 meters per second squared. Compared to free fall gravity of the planet, 10 meters per second squared. Looks like that coefficient of friction is 0.67. There you go. So the car can slow down at a rate that's about 2/3 of the gravity of the planet. What if you did this? What if you took same car, same tires, same road material, but you moved it to a planet like Mars that has about 1/3 of the gravity of that Earth does? Right? So pretty weak gravity on Mars. And the car starts with the same initial velocity, slams the brakes. Would it take more time and more road to come to a stop, or would it take the same amount of time, same amount of road on Mars where the gravity is really weak? It would take more road and more time. Yeah, because if you turn down, let's say, go back up to like this line here, right? If you take that gravity, turn it down for the same coefficient of friction, yeah, the car is going to slow down at a lesser rate. Yeah, would be true. Double braking on Mars. All right, you guys feel pretty warmed up for physics. That's a good quiz review too. Okay, so let's go back to this very down frame. Show you guys how to finish this off. You guys got to start on this on Friday, and then it was a short day. You got cut off a bit. So remember, you guys had these red pulleys, and you were using those to mark the locations of, well, either where you're getting the materials or where you're shipping everything to, the forest where the wood's come from, the copper mine where the copper's coming from, and the town where the manufactured goods are being shipped to. Right? Tie strings, tie weights, and then adjust the weights according to transportation costs, so it'd be proportional, and the equilibrium point of the factory will show up. So I gave you guys an example where I filled in all the numbers already, which is exactly this picture. This picture exactly corresponds to my example. Okay. 3 transportation costs proportional to each other, 3 locations, and then the factory location will show up naturally. Okay. Right, so you guys have got this started, got scenario A, got scenario B is completely open. You can make up whatever costs you want, you can make up whatever locations you want. And then on the back, what I want you guys to do is just take one of your setups. You don't have to change anything. Just pick your last setup, for example, and take one of those strings and align it to an axis. Maybe call this like one of the axes, either X or Y axis. Right, so it looks something like this. Okay? And I say, okay, well, I'm going to measure what are these angles relative to the other axis. Right, so alpha and beta. Got alpha and beta. So break out your protractor, measure those. Okay? Measure what are the tensions in the string. Now I call it force A, force B, and force C. Force A, force B, force C. But those are tension forces, right? Now there's 2 ways you can get the tension forces. There's sort of a quick and dirty way to do it. Is just say, well, what's the lab weight that's hanging over this pulley on the other end? Because it should just be equivalent to that. So, for example, if you had one of these hanging over the edge, this is 500 grams that weighs about 5 newtons. You could call that a 5 Newton force. That's okay. But if you did want to be more scientific about it, the way you would actually do that is you break this apart right here. You throw in a spring scale, like right there. And then this would stretch out to like right about there. And you say, that force is rating 5 newtons. And then you could get more scientific about it. So it's up to you. You could either say 5 Newton weight hanging over the edge, this must be 5 newtons, or you could throw in a spring scale and measure it that way, directly that way. Okay. So these last couple of boxes, there's a couple of equations. It says what's the net force in the x direction, what's the net force in the y direction. Now this is all based on the last class that put this together. I think there's a little confusion about this. So let me zoom in with the camera. Because if the factory is in equilibrium and it's not moving at all, it's just kind of sitting there, then what should the net force in any direction B on that factory. If it's at rest. Net force is 0, right? And what I'm trying to show you here, what the point of the setup is to say that that's also true in any particular direction, along the x-axis or along the y-axis. So, kind of like 3 monkeys pulling on bananas. You guys remember 3 monkeys pulling on bananas? Doesn't that look almost exactly like this? Right? So, how do you get the forces in the x direction? Well, isn't it some kind of cosine relationship with either one of these angles? Like this force times cosine of alpha would be to the right, and this force times cosine of beta would be to the left. I bet those should cancel out. I wonder if they do. I bet they should. See if they do. You guys can calculate each one of those by taking cosines. Okay? And then the forces in the y direction. Well, this would be a sine relationship. This force times sine of alpha, and then this force times sine of beta, both saying, hey, let's go upwards. That should balance with this force C pulling down this way. So, yeah, see if it does or how close that comes. Right, you guys got any questions about this lab? Right, so just like back on Friday, I will leave this diagram up on the projection so you guys can reference it if you need to. You guys got the rest of the class to finish this page and turn it into the Great Trade for points.